So yes, I'll move to the whiteboard as we go along. So let me just recap what I talked about yesterday. So here's the basic picture I want you to keep in mind. We're studying some problem with some multiple set of critical points or singular points or special points in some way. The sort of motivation of resurgence is to understand whether or not, in some physical example, there are explicit relations between the fluctuations around the different points, and whether you can use that to learn something interesting about the physics. So I talked about some examples in differential equations. I want to finish off the area function example, and then we'll go to look at some nonlinear differential equations. So let me just remind you what we did at the end yesterday. Here's the area differential equation. So this is a cartoon version of trying to do perturbation theory in a problem. Given this differential equation, it's very easy to develop the large X expansions. There are exponential behaviors with a prefactor. So this is the sort of standard saddle point approximation, if you like. But then there's a full series of fluctuations around those two exponentials. And from this differential equation, you can write a recursion formula for those coefficients. And you learn that they're just these factorials. And this is factorially divergent because there are two factors of a factorial on top and one on the bottom, so the net growth is factorial. If you look at this expression on its own, it looks as though changing the sign of x to the 3/2, which is a rotation of 2 pi over 3 in x, it looks as though you just interchange these two series, right? Which looks as though you would expect that AI rotated is just the BI function up to some overall factor, right? Turns out that's not correct. There's an exponentially small, compared to this, correction, which is the non-perturbative part of this connection formula, this analytic continuation property of the function whose asymptotic expansion you were trying to use, okay? So the strategy here is, suppose you didn't know this about the function you're trying to calculate. Suppose you only knew the asymptotic expansion. Could you somehow learn about this? Okay? And we went through the Borel summation of this, and we can indeed do this because if we construct the Borel transform, here we divide the coefficients by n factorial, use the Borel transform variable t. It's a hypergeometric function, and that function has a cut in the complex t plane. And if you form the inverse, so you integrate over t, you just recover this original series back here. But now, because this integral has a cut along the negative t-axis from -1 to -infinity, when you start rotating x and compensate by rotating t in the other direction, you end up integrating along that cut, and you're either above the cut or below the cut, depending if you rotated this way or that way. And so the difference between the two uses the discontinuity of that Borel function across that cut. And the remarkable fact is that discontinuity is again the same function, but with a shifted variable. So if you process that through, you learn that this function rotated by 2 pi over 3 compared to rotating the other direction by -2 pi over 3, the difference between the two is given by some integral of this guy, which is the same function back again, but with an extra exponential because of this 1 minus t business, change of variables there. Okay, so I'm not going to go through more detail than that. It's an exercise for you to just fill in the steps. But you see where this extra piece comes from, and that corresponds to this extra exponentially small piece here. Okay? So that the message is that that information is contained in the Borel summation of the asymptotic expansion. Whereas if you just look at the series itself and try to analytically continue that off the real axis, then you would miss something. Okay, so now I want to solve this problem another way, which I would say is the sort of analog of doing it from a path integral perspective. So imagine you were trying to calculate some quantity not using a Schrodinger equation or a Klein-Gordon equation or Dirac equation. Imagine you were trying to solve a problem using a path integral representation of the thing you're trying to calculate. So now you're back in the problem that I mentioned at the beginning yesterday, that you have some path integral which has an I in it, so it's very poorly defined. There's nothing you can do with that integral numerically. And so the analog with lattice gauge theory, people trying to do a functional integral with an I in it, is that they can't evaluate with Monte Carlo. But of course, here we know that the first step is to rotate the contour in some manageable direction. So let's just go through this in detail. So remember, t is the integration variable, but x is the argument of the function we're trying to calculate. Okay? So the first thing to do is to just clean this up a little bit so that x appears outside as a large parameter. So let me write x as a real part multiplied by a phase. So we're going to be interested in the real part being large, in which case we do asymptotics, but we want to be able to rotate the phase of this parameter x. And in particular, I want to be able to rotate from x on the positive real axis all the way to x on the negative real axis. Okay, so let's do, if we change variables like this and then we rescale the integration variable by a factor of root r, the integrand now looks like this. And now I put in an I, so I'm now integrating along the imaginary axis. Okay, so here's the large parameter. This is my action. And there's a parameter which is just the phase of the variable x. Okay, so how do we do this? We have to decide what are the allowed contours for an integral like this. So when I integrate over z out to infinity, this is the complicated piece. So I need z cubed to be positive asymptotically, okay, for this to be well defined. Which means I can go along the positive real axis, or I can go at 2 pi over 3, or at 4 pi over 3, okay? So any contours that end in those regions are well defined. And there are 3 such contours that I can draw, and I can construct an arbitrary contour by just taking linear combinations of these. Okay? So now we're going to study the saddle point analysis of this type of integral. So where are the saddles? All right, we're just looking for critical points of the action, so to speak. So that says that z squared is e to the I theta, is the critical point. Remember, we want to do this as a function of theta. We want to allow theta to vary. So the saddles are at plus or minus e to the I theta over 2. And they move around in the complex z-plane as theta varies. The next thing we have to do is we have to evaluate this action on those saddle points. And that gives you this factor here. Plus or minus, depending which of these 2 saddles, r to the 3 halves, and then e to the 3i theta over 2. Okay? The next thing we have to do is we have to decide what are the steepest descent contours which pass through those saddles. So remember, the definition of a steepest descent contour, it's a contour in the z-plane such that the imaginary part of the exponent, so the imaginary part of the action, stays constant. Right? It's the definition of a steepest descent contour. But we also want them to go through the saddle points. So the constant value along these steepest descent contours must be equal to the value at the saddle point. Right? Clear. So since that's the action, the imaginary part of that action at the saddle point is just given by this. Is that good? Okay, so remember, theta is a parameter that you can vary at will. So this is just a parametric equation for those steepest descent contours, okay, in the z-plane. So I was going to do this in real time, but unfortunately something's wrong with my Mathematica. So I'm just going to show you some plots now of what these steepest descent contours look like as you vary theta. So when theta is 0, so up here is going to be the value of theta in units of pi. So when theta is 0, the saddle points plus or minus e to the I theta over 2. So when theta is 0, the saddle points are at plus or minus 1. And the steepest descent contours are these. The colors are completely different from my colors here, but okay. Right, these are the steepest descent contours going through, and the transverse ones are the normal ones, with normal meaning perpendicular ones, that are the steepest ascent paths. Okay? So, and these shaded regions are the allowed regions of my contours for which this integral is well defined. Okay? So remember, my integral originally was going now along the imaginary axis. So in this case, I would deform that contour to this curve, goes through this saddle point, ends up in the good region, so that's a well-defined integral. And so when theta is 0, so remember x is now positive, one saddle point contributes. Okay? And that's why you have the exponential decay when x is positive, governed by one saddle point. But now let's change theta. Let's increase theta a little bit. So we're taking x off the positive real axis into the first quadrant. So I was hoping to do this continuously, but it wasn't working. So first of all, the saddle points moved. They rotated. They're now at e to the I pi over 4 and e to the 5 pi over 4, these circles here. And here's the steepest descent contour. And here's the other steepest descent contour, ending up in the good regions. These other ones are just spurious curves from Mathematica nonsense. Try to ignore those. So now my integral is still the one that was along the imaginary axis. I still deform it here, and now this is the saddle that contributes, and that gives me the correct answer. Now let me increase theta so that it's almost at 2 pi over 3, because we know that 2 pi over 3 is the interesting point. So the next plot is going to be just below 2 pi over 3. So now this steepest descent contour goes through this saddle, goes near the other saddle, but then goes like this. And the other one is going like this through that saddle into the good region. But again, at this point, only one saddle contributes. Still, I just deform my contour from the imaginary axis to go like this. Okay? Now I'm going to jump a little bit more in theta, and you'll see that the second saddle suddenly starts to contribute. So now, remember, I wanted to go like this, and so I go up like this, but now I go to the right of that saddle into this region. But if I want, my original integral was along here, so I have to do this followed by this. Okay? This jump, this so-called Stokes jump, occurred when theta hit 2 pi over 3, which in the original x-plane, as you're starting on the real x-axis, you're rotating. Remember, we're aiming to go to x equals negative. But when it hits 2 pi over 3, suddenly this second saddle starts contributing to the integral. And now if I keep going, rotating even further, you see it's now even clearer that I have to go like this and this. And so to do this saddle point approximation, it's not even the approximation, it's the definition of this integral in terms of these deformed contours, I have to now include both of the saddles. And now when I get all the way to the negative axis, the saddle points are now on the imaginary axis. They're now at plus or minus I. Theta is now pi. So the saddles are sitting right here and here. And now we have this nice symmetric configuration where you have to add those two contributions. And that's why there's a sine type behavior, the oscillatory behavior along the negative x-axis in the Airy function. Okay? So this, at a certain level, this is trivial because it's a simple linear equation. But there's a lot of physics in this equation. So if you're unfamiliar with this, I really urge you to work through it yourself and just become familiar with it. The deep questions are the following. When does some saddle appear or disappear? We saw that's happening here. In other words, as a function of this external parameter x, how do I know which saddles contribute to the integral? And not just that, when they contribute, so they contribute with the value of the function in the action, but there's also a very important phase factor. Right? The angle at which these things go through the saddle is important, because remember, the behavior at negative x is not just the sine of 2/3 minus x to the 3/2. It's sine of that plus pi over 4. Okay? And that plus pi over 4 is a phase difference between the two saddle contributions. Okay? So now imagine you're trying to do this in a functional integral. First of all, you have to somehow work out what it means to have steepest descent contours. You have to somehow find, first of all, you actually have to find the saddles. Then you have to find the steepest descent contours through those saddles. Then you have to decide which of those saddles contribute to the thing you're trying to calculate. And remember, the answer to that question changes, or you should expect it to change, as you vary parameters appearing in your functional integral. Right? And then, even once you know which saddles contribute, you have to know the phase factors, relative phase factors. If there's only one saddle, you don't really care about the phase factor sometimes. But once there's more than one, the relative phase is extremely important. Right? And those are the really complicated questions when you start going to multi-dimensions or infinite dimensions. And that's the general story of Picard-Lefschetz theory and Lefschetz thimbles. And I'll say some more about that as we go along. But you already see that this is an issue, and that it's an interesting issue, from this Airy function example. Okay? And that's why I wanted to go through this in a lot of detail. Any questions at this point? So the reason the Airy function is so important, apart from applications in optics, is that when you think of WKB, the Airy function describes the generic situation of a single turning point. Right? And that's why the Airy function is so important in non-perturbative physics. Okay? And the problem we're going to do next is going to be the nonlinear version of this. Yeah. Yep. Just before? Yep. This one? So, no, this one is perfectly well defined, but it's not part of your original integral. Because my original integral was this, and the question is, how can I turn that integral into something well defined? And the answer is, well, I can just turn it into that guy. But now I have to add that bit over here. So in terms of what it means is there are three basic guys, and I can build my original integral out of some linear combination of these. And what's called monodromy is that the contributing ones can jump as you change the external parameter. Okay, so there's sort of a basis of allowed paths, and your particular integral that you started with, I started with the Airy AI function, but I could have started with the integral representation of the Airy BI function, and it would have been a different set of paths. Okay. So again, that's actually an important point. It also depends what you're calculating. So you could have a functional integral for a theory, but you might calculate one quantity for which the answers are these saddles are important. You may calculate another quantity, and different saddles may be important for that quantity. Okay. Okay, so one more little piece of terminology here. Let's not get confused. Those pictures here were in the plane of the integration variable. Now let's draw a picture in the external parameter x, so the complex plane of x. So when x was real and positive, theta was 0, and the actions were real. They were either plus or minus. And lines along which the action is real are called Stokes lines. So there you have a large exponential and a small exponential. So a dominant large exponential and a subdominant small exponential. But if you go along the pi over 3 or pi or minus pi over 3 directions, along those directions, theta is such that the action is now pure imaginary. So now your two exponentials are e to the I something and e to the minus I something, and they have exactly the same magnitude. Okay? So here's the issue in the x-plane, is that you can start here and one of your exponentials, one of your non-perturbative saddles is dominant and the other one is subdominant. As you change the angle, the subdominant one, if you like, becomes more and more important. And when you reach this anti-Stokes line, each of the two non-perturbative contributions is equally important, and you're not allowed to neglect one compared to the other. Okay? So the idea of a Transseries and of this Stokes phenomenon is that in order to have the full analytic continuation structure of the thing you're trying to calculate, you need to keep track consistently of all of the non-perturbative saddles and understand how they vary as you vary parameters. Okay? So I want you to think of this in the back of your mind. Think of the sign problem for QCD, where there's a parameter which is a chemical potential, which is the thing that is making the action complex. Okay? So it's the thing that means, that causes the fact that you can't just use straightforward Monte Carlo. Now, as you change the density, you can have a phase transition. So if you think of it in this sort of thimble saddle language, as you change some physical parameter, such as a chemical potential, that's like changing theta. Okay? So you should expect that at certain points, as you change density, saddles can come and go, disappear and reappear, and even be more relevant for calculating some particular quantity or another quantity. And the physics idea here is that those things are a way to interpret and to find phase transitions. Phase transitions can be understood as the Stokes phenomenon of the change of dominant saddles. Okay? Okay, so I just said that. So one more thing. We talked yesterday about this large order, low order behavior, that the large order behavior of the coefficients around one of these saddles told me the low order coefficients about the other saddle. So let me just show you how that works here for the Airy function. So here are the coefficients. By the way, the reason it's 4/3 here, can anybody tell me immediately why it had to be 4/3 to the power n there? And not some other random number? Remember, this is just from perturbation theory. This is not from deforming contours. 4/3 happens to be twice 2/3. Okay, I think we can all agree on that. Okay. And remember, the exponentials were plus e to the plus 2/3 x to the 3/2 and e to the minus 2/3 x to the 3/2. So 4/3 is the difference between those two saddles. Okay. So that's interesting, and that we'll see that again and again as we go along. So here are the first few coefficients. Clearly, they're growing like n factorial because there's n factorial, and an n factorial. And if you look at the large order behavior, there's this stuff here, and there are the first two numbers. And you will see immediately that they don't agree with those two numbers. So what am I talking about? And the answer is, if I put in a factor of 4/3, it does agree with that. So 4/3, 5/48 is 5/36. So there's an extra, remember there was an extra factor of the action difference. But now the next term doesn't agree, but that's because it shouldn't be 1/n, it should be 1/n minus 1. And the difference between 1/n and 1/n minus 1 is of order 1/n squared. So once you add that extra bit and put in 4/3 squared, now you see that number. Okay? So this large order, low order relation is really encoded there, but you have to know what to look for. If you just look immediately at the large order growth, you don't see it. You have to put it into this form, where there's an extra factor of the action difference at each order, and it's in powers of 1/n minus 1, 1/n minus 1, n minus 2, etc. Okay? Again, I urge you to play with some special functions just to see that this structure always happens. Okay, so the Airy function is important, as I mentioned, because it's the universal behavior of a turning, in the vicinity of a turning point. So now we're going to look at the nonlinear version of the Airy function, and we'll see that new things happen, interesting things, new things happen. And it turns out this nonlinear Airy function, called one of these Penlevet functions, is a universal function in matrix models and in certain models of string theories. And so I want to go through some features of this system. So for a start, let me just say a few words that I mentioned last time, that if you have an nth order linear equation, there are generically n different exponentials that contribute. So for second order, that's obvious from WKB, there are 2 different exponentials. If you go to third order, an easy way to get a third order equation is you just multiply 2 solutions of a second order equation. That satisfies a third order equation. But now if you have 2 exponentials, multiply 2 exponentials, the net result is 3, right? There's a cross term. So there are 3. And that's generally true for an nth order equation. But for a nonlinear equation, as soon as you have one exponentially small contribution, because of the nonlinear term in the equation, you must get all powers of that exponential. So you immediately now see in nonlinear equations we'll have an infinite number of saddle points to deal with. And that can be one of the origins of some interesting new features when we go to nonlinear equations. So there's a set of equations called the Penlevet equations that are the generalization to nonlinear equations from the familiar special functions of linear physics. So when we solve standard problems in electrodynamics and classical mechanics, we're always dealing with Bessel functions and hypergeometric functions and whatever. And these are the special functions satisfy standard second order linear equations. You can actually classify the second order nonlinear equations that have the special property that they're so-called movable poles, which correspond to boundary conditions. Sorry, they're movable singularities, which correspond to boundary conditions, are only poles. They're not branch cuts or essential singularities. And those are called the Penlevet equations. Remarkably, there are only 6 of them, and they contain everything such that you only have movable poles. And they show up everywhere in physics. I mean, the whole theory of integrability is built on these functions, very, very deep connection to integrability. And essentially, any dimensional reduction of the self-dual Yang-Mills equations, Einstein equations, that boils down to a ODE that you can solve is an example of one of these Penlevet equations. So they're worth studying, and they show up a lot in the type of physics we're talking about at this school. So I'm going to talk about Penlevet 2. There are 6 of these equations, Penlevet 2. And it's actually a special case of Penlevet 2. Penlevet 2, I can add a constant to this right-hand side if I want, but I'm going to talk about this one. And you see it's a nonlinear Airy function. I'm going to start doing stuff on the board, but for now, you see that this is the Airy equation, but I've added a particular cubic nonlinear term to it. Okay? This particular equation shows up all over the place in all sorts of models, not just physics, in mathematics. Here's a random list. It's very standard for double scaling limits in matrix models and in 2D gauge theory type models. It also has purely combinatorial and probabilistic interpretations. So this list could have gone on forever. And it's universal in the sense that the area function is universal, in the sense that it's a behavior near a turning point. So what I want to do now is to analyze how you would solve this problem. So the first thing is, let's look at x at plus infinity. And let's look for a solution that goes to 0 at plus infinity. So if it's going to 0 at plus infinity, then y cubed is much smaller than y, and much smaller than x times y. So the first thing you have to solve is the area part, which it linearizes and becomes some parameter times the area function. Right? That's the first step. So the requirement that you want a solution that's decaying at x equals plus infinity tells you you have the area function with an unknown parameter. And we're going to see that this unknown parameter is an instant-on counting parameter. But at this point, it's a linearization parameter. And that area function is already exponentially small. Right? At large x, it has an exponential factor multiplied by a fluctuation series. So it's purely non-perturbative in that sense. So how can I go beyond that and study the plus dot dot dots? So the idea would be to write y as my first order thing, which is that sigma times the area function, plus, and might as well just be honest and write it as the area function. Plus something that's much smaller than the area function. Okay? So now let's plug that into the differential equation and expand to linear order in the much smaller quantity. And you learn that delta y double prime is equal to x times delta y plus 2 sigma cubed ai cubed, I don't need the x, plus, etc. Okay? So now look at this. This tells you that delta y must go like the area exponential e to the minus 2/3 x to the 3/2 cubed. Right? Because otherwise there's no way you can balance this with this. Okay? So the area function is exponentially small. Delta y must be essentially the cube of that. So it's much, much smaller. So that means, if you think about the next term, that means that I should write this as sigma cubed times, let's call it y3, plus sigma to the 5th y5 plus dot dot dot. Okay? You can plug that into the equation, expand, compare powers of sigma. Remember, sigma is just a number here, which we haven't determined yet. And you'll see that this is a consistent scaling. And the consistent scaling is that this thing here goes like e to the minus 2/3 x to the 3/2 with some prefactor stuff. And this thing here scales like that, etc. Okay? So the full solution to this problem is in fact, and these are multiplied by fluctuations. So the full solution to this problem is in fact one of these Transseries that I was telling you about. The full solution y has the following structure. It's a sum k equals 1 to infinity, and there was this minus x to the 1/4 business, there's a sigma here, raised to odd powers, okay, only the odd powers, and each of these is multiplied. It's not exactly the same one because I pulled out these factors, so let's just call it fk of x. So those are the fluctuations in the k sector, k instanton sector. Okay? So that's a consistent scaling, and you can simply plug that ansatz into the equation, expand in sigma, match terms, and you see that the original starting point is just the area equation, which we studied already. And now y3 is just a linear equation, but with an inhomogeneous piece that comes from area function q. Okay? So that thing is completely determined by the previous exponential. And once you work out y3, if you try to solve the equation for y5, it's also a linear equation for y5 with an inhomogeneous term that involves both y1 and y3. So the fluctuations involved in y5 are completely determined by the previous two instantons. Okay? So this is organizing the solution as a Transseries that involves exponential terms mixed together with asymptotic series that are the fluctuation terms around that instanton. Okay? And now you see that there's a parameter here, because this was a second order equation. There have to be two boundary condition parameters, right? We used a parameter by saying we wanted a decreasing solution. So in the linear level, we killed the bi function. Right? But there's another parameter somewhere. And the other parameter is sigma. And it's called a Transseries parameter. It's its technical name. It counts the order, the exponential order of the Transseries. But to us, we can think of it as an instanton counting parameter. And what it is, it's the boundary condition parameter. It tells you that every solution to this equation at large x decreases like an area function, but some multiple of an area function. And any multiple is okay. Okay? At plus infinity. But that multiple reappears in powers when you go to these higher exponential orders. Okay? Clear? So that's, we'll see. Now the interesting, this is at plus infinity. So everything at plus infinity is falling off very fast, but multiplied by some number that we can't fix yet. Is that good? All right, now let's look at the other side. So this, I've just done this. Here's the Transseries expansion. Sorry, why did I put a minus here? Somebody should have told me. Okay, now let's look at the other side. Let's look at x goes to minus infinity. As x goes to minus infinity, now we can choose our boundary conditions, and suppose we choose to have a smooth solution. So a smooth solution is one where the derivatives are small. And so I'm actually going to balance this term against this term at minus infinity, which means that y squared, as x goes to minus infinity, so this is the behavior as x goes to plus infinity. As x goes to minus infinity, y is going to go like plus or minus the square root minus x over 2, 1 plus something. Okay, that just comes from balancing xy against 2y cubed. Okay, so you can now just plug that in, and you discover, I don't know if I have it here. Yeah, I do have it here. So it's just a matter of inserting a 1 plus inverse powers of x, and you just plug it in, and you generate a recursion formula that'll spit out all these coefficients for you. Okay? Nothing complicated. could have done this in kindergarten. Right? And remember, x is negative, so I'm going to have powers of minus x here. And there are just some numbers. Okay, so somebody please tell me what's wrong with this expression. That can't be the answer, right? There are two reasons it can't be the answer. Sorry? No, this is supposed to be the behavior at minus infinity. There's no parameter. Okay? All those numbers are just completely determined. There's no boundary condition parameter. So this cannot be the answer. Right? So where's the other parameter? In perturbation theory, you don't see this other parameter. It's hidden. That's one reason. The second reason is, if you go on further, you'll discover that these coefficients grow factorially. And you'll also discover that all of them are negative numbers. And if you remember what we talked about yesterday, if you try to do Borel summation with some coefficients that are all the same sign and are growing in magnitude n factorial, and you apply Borel summation to them, you'll generate an exponentially small contribution, but which is imaginary. Okay, so I didn't say, but I'm actually looking for a real solution here. So that's another thing. We're missing something because these are non-alternating and factorially divergent. So there are two reasons to be suspicious of this. So what can we do about that? So first of all, let me write this one here. This is plus 1 over 8x cubed minus da, da, da. So what we can do is we can again, now that we suspect that we're missing something non-perturbative, we can again write y as y perturbative plus delta y, where delta y is going to be smaller than any power, so it's exponentially small in some, as we expect. So now let's insert this in the equation to linear order in delta y. So we'll get y prime prime plus delta y prime prime is equal to xy. So p is perturbative. And then I'm going to get here, I'm going to get 2yp cubed plus six yp squared delta y. Okay? Plus higher order terms in delta y. Okay, so yp is the solution to this equation, so we can drop those terms. So what we're left with is that delta y prime prime goes like x plus 6 yp squared delta y. I'm doing this slowly just to show you how easy it is. Now, at large negative x, yp squared is going like x. So it's the same order as this thing. Okay, so I have to keep it in relation to that. And in fact, if I keep the next term, I find that this thing is minus 2x. And then I think it's minus 3 over 4x squared. If that's wrong, I'll discover it in a second. Right. Okay, so let's look at the first term first. All right, it's minus 2 because there's a plus 1, but there's a minus 3 from here. on. I'm a little worried about something here. Yes, okay. Sorry, the issue is that I'm going to write this as plus minus x, because we're talking about x negative here. Okay? So you see that that tells you immediately that delta y goes like e to the plus or minus root 2 2/3. And if you include this term here, and it's a linear equation, so I can't fix the coefficient. Okay? Because of the 2 here, there's an extra factor of root 2 there. Okay? Now that's not a typo if you compare with this and this. Remember, for the Airy function, on the positive x side, it was e to the minus 2/3 x to the 3/2. And on the negative side, it was e to the I 2/3 minus x to the 3/2. But they were the same 2/3 in the exponent. In this case, because of the nonlinearity, the exponential on this side, where x was positive, when you go to x negative, it's a different instanton. It's a different action. There's an extra factor of root 2. Okay? So what's happening here is that as you approach from plus infinity, at plus infinity, the sort of one instanton expression is a good approximation. As x becomes smaller and smaller, these exponentials become larger and larger, of order 1. As you approach x to 0, they're all of order 1. And to approximate the function with that Transseries, you need all of them. You need all orders of the instantons. Now when you cross from x positive and you want to match it to something coming from x negative, these have to match up, and this complicated condensation of instanton phenomenon comes out on the other side with a different instanton action. And we'll see later that we'll be able to see explicitly that this is a change of saddles in this problem. That the saddle governing on the negative x side is just a different saddle, and it has a different action by this factor of root 2. And this phenomenon governs certain phase transitions in matrix models and 2D gauge theories, and you see it already in this simple behavior, simple to derive, not simple to understand, behavior in this nonlinear equation. Okay? So we can do better than that. Once we know that that's the starting point for this delta y, I can also plug in and work out what the corrections are. Okay? I just insert that ansatz, put it into the equation, start expanding, and you learn some numbers here. Okay? And you learn that the expansion is in expansions in powers of minus x, not cubed, but minus x to the 3/2. All right. Now, we're going to use this formula from yesterday. I'm going to make a prediction from this expression. I'm going to make a prediction for the large order growth of those numbers. Okay? So this is working backwards. What we talked about yesterday was having the perturbative series large order behavior predicting the non-perturbative. Now I'm going to use this non-perturbative leading term to make a prediction about the large order growth of those coefficients. Okay? Using this formula, this Borel formula. Okay? So what we need to do is we need to rewrite, first of all, this exponent. We need to rewrite it in this language, and I want to identify these parameters. Okay? So first of all, let's look at the exponent. The perturbative expansion parameter is minus x cubed, or 1 over minus x cubed. So root 2, 2/3 minus x to the 3/2 is minus 8 over 9 x cubed to the 1/2. I think, yes. Okay? Now remember, here x is a large parameter, so x is like 1 over g. Okay? So that tells me immediately that gamma is a half. 2, sorry. Gamma is 2. 1 over gamma must be a half. Now I can also work out what beta is. Beta is 9/8, because remember the parameter is 1 over x cubed. If you then look at the prefactor, which I'm not going to do, I'll leave that as an exercise for you, you learn that delta is minus 5/2. Okay? So all we did was we had some way of estimating what this leading non-perturbative contribution would be. Imagine you had some semi-classical or WKB argument for calculating that quantity. From that quantity, just looking at its scaling, I can tell you what those numbers should be for the large order growth of the perturbative expansion. Okay, so let's check that. So here on the next slide, this is sort of an exercise for you to check these quantities. So the prediction is that these coefficients in the perturbative sector, these guys here, are going to grow like gamma 2n minus 5/2 with a power of 9/8 to the power n. And moreover, I can predict the subleading terms from these numbers here. Okay? Because here I have 1 extra power of the action, 2 extra powers of the action. So I put it into that form that I want. And so I know that this is going to be the subleading large order growth. So this is actually quite impressive, actually. From just a simple scaling argument of this exponentially small next contribution, which is a more or less one-line calculation from the differential equation, you can make a prediction for the leading and then subleading growth of the asymptotic perturbative perturbative asymptotic expansion. Okay? And you can now go and check it, that in fact this is the leading growth, and these, you can be even more precise, generate lots of terms. It's easy, you just generate a recursion form. You can generate hundreds and thousands of these terms, and just check that that's the leading growth and this is the subleading growth. Okay? So message, I gave you some examples of this low order, large order relation, and you might have been suspicious that this was just some weird feature of these simple linear equations like Airy functions and hypergeometric functions and whatever. You might have thought that there was just something special about these very simple linear equations and there's no way it will apply to more complicated problems. The answer is it always happens for any differential equations. Okay? Linear, nonlinear, it doesn't matter. So if you're not convinced by this example, I urge you to pick one of the other Painlevé equations and just do the same analysis. It's easy. All you need is Mathematica to generate many terms and a little bit of analysis like this. Okay? And again, I picked this example because it shows up in a lot of problems in the type of physics we're interested in. That's from this sorry, I have to go back a lot. So this formula here. In this case, we now have effectively an infinite number of saddles because it's a nonlinear equation, right? And this statement says that I can study the leading behavior and the subleading corrections from the contributions from the other saddles. Okay? So if you, those are the differences between these exponentials. So they're just multiples of this. It's the only thing they can be. It was just the statement, if you can represent the function with a Borel integral, then the Borel integral has some singularities. And by deforming the Borel contour integrals around those singularities, you learn that the fluctuations around those singularities are related to one another in this generic way. So what we did here is we identified the next singularity, the e to the plus m, this one. And we can then use that in reverse to make predictions how the what the large order growth of the one around the other perturbative saddle behaves. Okay? And again, you might have thought that only works for these linear equations. This is a proof by example that this applies in these. And I could continue. This was just the first saddle. There's an entire network now of structure when you go to the higher saddles, how they relate to the other ones. Okay? And that's all understood. The way to organize that calculation when you go to these higher saddles is something called, it's a bizarre name, called alien calculus. It's a way of sort of controlling these networks of relations for these nonlinear equations. Yeah.
So, Transseries you wrote yesterday that contain log
Yeah. Yeah, so the Transseries solutions to this particular equation doesn't involve log term.
So this is the special property of plane leap 2.
Say it again.
So the fact that the Transseries doesn't involve any log here is a special property of plane leap 2 ODE.
No, it's actually a general feature of differential equations that the way you generate logs in these differential equations is by tuning parameters to have resonances between the different saddles. And in this particular example, there isn't such a resonance.
So this is not a property of the differential equation.
This is a feature of this particular differential equation that you won't see logs. Okay? So this is the first example of a Transseries structure coming from a nonlinear equation. I wanted to keep it relatively simple to start off. Okay, the other interesting thing about this equation, now imagine we try to connect these two. We've decided that we have a Transseries at plus infinity, where is it? That's in powers like this with fluctuations. And the Transseries at minus infinity is in terms of powers of this guy with fluctuations. Okay? And they're not independent because I want to tie them together now. And remember, the leading behavior at minus infinity was this square root type behavior. And at plus infinity, it was this rapidly falling off area function behavior. Now imagine you want to tie them together and match them. Remember, there was one parameter here, which was sigma, which we're free to adjust on the right-hand side. And there's another parameter here coming with this. There's a coefficient in front of this exponential. So there's a parameter on the left-hand side. So you can tune those two parameters such that they meet, and meet smoothly. And there's one and only one choice of these parameters such that they meet, and it's that this coefficient sigma is 1. And here's a plot of what happens if it's a bit bigger than 1, and what happens if it's a little bit smaller than 1. This is a nonlinear equation. It's unbelievably sensitive to that choice of parameters. So in other words, if you try to numerically integrate this equation, starting at plus 50, right? Pick some random number, right? And you force it to be some number times area function at that point. And then you numerically integrate downwards. Unless you tune that coefficient to be exactly 1, at some point at negative x, it'll either go like that or it'll go like that. This is an example of a separatrix. this curve here is a separatrix. So exponential sensitivity to boundary conditions of whether you can really land on this separatrix or not. Okay, so there's a big literature on this in the mathematics literature. From the physics point of view, the interesting thing that's happening here is that you're getting a different saddle, a different type of instanton on one side and the other. And I'll show you later, tomorrow, maybe Thursday and Wednesday, that it's a change from a real saddle to a complex saddle. And the phase transition happens at this x equals 0 point. And this is exactly the double scaling phase transition in the unitary matrix model. But you can identify this in many, many other models because this is universal. This is the behavior of crossing a turning point in the nonlinear language. Okay. So it's condensation of instantons. Okay, so I finished lecture 1. Okay. All right, so now let me proceed a little bit. Okay. I'll probably get bored and turn this off in a minute. But, so let's start trying to go beyond differential equations and get to something more interesting, some quantum mechanics, functional integrals, or field theory. So a very important argument was proposed by Dyson in the early 50s. If you haven't read this paper, I strongly urge you to read it. It's about 2 pages long. There's either 1 or 0 equations in the paper. I can't remember whether it's 1 or 0, but it's certainly less than or equal to 1. And the argument is this. Could perturbation theory for QED be convergent, or do you expect it to be divergent? And remember, the best we have at the moment, the state of the art, is the 5th order calculation of the anomalous magnetic moment, G minus 2. The 5th order calculation involves more than 13,000 5-loop Feynman diagrams. Okay? Not all of which can be computed analytically. At 4-loop, they're actually now computed completely analytically. It's amazing. There are 981 diagrams at 4-loop. At 5-loop, many of them are computed numerically, but we have the answer to maybe 5 digits or something like that. Going to higher loops, okay, it's not going to happen very soon. So we need some other way of looking at the problem. So Dyson came up with this extremely beautiful argument of why you would expect an expansion in alpha, or let's call it E squared, H bar and C take them to be 1, why you would expect this not to be convergent. Okay, so imagine you're computing some quantity, such as G minus 2. The answer is a series in alpha, so it's a series in E squared with some coefficients, right? Now suppose that expression was convergent. That means that in the complex E squared plane, there's some circle around 0 of some non-zero radius, I don't care what it is, but it's non-zero, inside of which essentially everything's analytic. Okay? That's not quite exactly what it means, but it's roughly what it means. Okay? The radius of convergence will be set by the nearest singularity. So if you stay within the circle, no singularities. Okay? So now on physical grounds, you can argue that that can't possibly be true, because as soon as E squared goes negative, no matter how small, as soon as E squared is negative, now like charges actually attract one another, and opposite charges repel. So if you tried to, so this is Dyson's argument. It's not a proof of anything, but it's an argument. If you tried to construct the QED vacuum where E squared is positive, so now you have to worry about vacuum fluctuations and charges and all sorts of nonlinear interactions from QED. And if you suddenly just flip the sign of E squared, but E squared was really small inside your radius of convergence, then Dyson's argument is that the physics just changes completely. So there's no way this can be smoothly connected to E squared positive. Okay? That's it. That's the argument. Therefore, if you accept that, the only way out is for there to be a cut that starts exactly at 0, not at some non-zero value. Right? You see the argument? So in words, I mean, here's exactly what Dyson said. For every physical state is unstable against the spontaneous creation of particles. The system, once in a pathological state, will not... So, it's kind of waffly, but I think more or less everybody agrees that this argument is correct. But let me just caution you that some very, very serious physicists spent about 10 years during the 1970s trying to prove this for QED. And to this day, there is no proof. Okay? Diagrammatically, it's an extremely complicated problem because in QED, there are both fermion loops and boson loops. They have opposite signs. There are rigorous results about phi cubed and phi fourth theory divergence because all the diagrams have the same sign. And so with some very sophisticated combinatorics, you can actually prove divergence. This was actually done even before Dyson's paper by Hurst and by Thierry. But once you go to a theory where some diagrams are positive and some are negative, nobody to this date has managed to construct a watertight combinatorial proof of divergence from the diagrammatic side. So here's an exercise, not one that I expect the solution by tomorrow, but maybe one of you people will solve this. Clearly, the diagrammatic approach is not the right way to think of this, because the expansion parameter is in fact alpha over pi, so that's like 1 over 400, 500, whatever, something like that. So from the argument yesterday of the order of optimal truncation, we don't expect non-perturbative behavior to set in until roughly 500th order, if it's growing like n factorial. Okay? So that's not going to happen anytime soon. So a better way to think of it would be this reverse argument here. Try to use some non-perturbative information to tell you about perturbation theory. So that idea has also been tried and not successful yet, but I think that's the more hopeful direction. Okay? So I really urge you to read this paper. It is not a proof. It's often cited as a proof. It is not. It is very clearly stated it is not a proof. It's an argument. It's a very convincing argument, but there's some interesting Feynman diagramology to be understood here. So there's a very beautiful example of quantum mechanics trying to understand this phenomenon. So this actually goes back to Arkady Weinstein in the 60s. Imagine quantum mechanics with a cubic oscillator. So this potential looks something like that, or reversed depending on the sign of lambda. So you look at it, and you know that if you tried to do perturbation theory around that point, and you tried to just perturbatively calculate the ground state energy, you know that perturbation theory will generate an expression for that ground state energy, but you know physically, just from looking at that picture, that there should be an imaginary part to that ground state energy. Okay? Because it's a metastable state. Moreover, you know the sign of that imaginary part because it decays. It's not that stuff goes into that state. So this issue about resolving what to do with the Borel pole is fixed by physics. Okay? So Weinstein's argument was, suppose you do perturbation theory. The perturbation is odd, so the expansion is not in lambda, it's in lambda squared. All right? Any odd power will just vanish in perturbation theory. So in the complex lambda squared plane, so I'm going to call Z lambda squared, when lambda is positive, when lambda is real, the potential looks like that. So if lambda is real, lambda squared is positive. So if you follow Dyson's argument, that means that there should be a cut along the positive lambda squared axis. Because that's the situation in which the problem is unstable. Right? All right, so now let's be very bold, and let's assume that that's the only singularity. Okay, so that's a big step, but it's presumably correct. So if that's the only singularity, I can use Cauchy's theorem to calculate the energy at some point in the complex coupling plane, or lambda squared plane, coupling squared plane. I can just write the Cauchy expression for that energy. And now if I assume that that cut is the only cut, I can deform that contour and wrap it around the cut. Now I have to make some assumptions about fall off in infinity, and that's to keep the mathematicians busy, to worry about things like that. But let's proceed. That means I can rewrite this as an integral of the imaginary part of the energy across the cut. Sorry, integral along the cut of the imaginary part, the jump across the cut. All right? It's just above and below the cut. Okay, well that's good, because now the coupling doesn't appear in here anymore, it appears here. So I can now expand in powers of z0. Okay? And when I expand in powers of z0, the coefficient of z0 to the power n is given by an integral, so take r to infinity, of course. It's an integral from 0 to infinity of the imaginary part of the energy across the cut divided by z to some power n. Okay? So far, so good. Now let's do some physics. Physically, you know how the imaginary part of the energy scales. Right? The imaginary part of the energy, just from WKB, well, there's going to be an exponential, which is some dx and you do some rescaling, where this is, say, through here, and this is some, just by rescaling x, you see that it goes like 1 over lambda squared, multiplied by some number, which you have to do an integral to calculate the exact number, but it scales like 1 over z. Okay? And if you do a little bit more work with WKB, you can work out the prefactor. So now let's insert that into this integral and say, when n is large, this thing is dominated by the behavior near 0. So let's say that the coefficient Cn is going to go like integral 0 to infinity dz over z to the n plus 1 of something that's going like e to the minus b over z. You can insert the prefactor and refine this argument if you like. And now let's call T 1 over z. Okay? So we just learnt that the large order behavior of the perturbative coefficients goes like n factorial, doesn't alternate in sign, and is divided by some number to the power n, and that number is essentially an instanton action number. Okay, it came from this WKB tunneling. Okay? It's a very beautiful argument. And this is an attempt to try to make sense of this Dyson-type argument in field theory. The point is, if you have some way of calculating, we used a tunneling argument, if you have some way of calculating some semi-classical object, some non-perturbative object, you can use this to make predictions, conjectures of how the large order behavior of the coefficients will behave, even without calculating many of those large order coefficients. Okay. So that's very nice. Related example, Carl Bender's thesis in the 1960s, they looked at the x to the fourth model. Now you can ask, perturbation theory in lambda, now the perturbation is even, so you need all powers of lambda. You can ask the question, how can you prove that perturbation theory must be divergent? It's actually very easy. Compare this case with this case. All you did was change the sign of lambda. So if you're just doing perturbation theory around here or here, perturbation theory couldn't care less what the sign of lambda is. Okay? There's no difference from the point of view of perturbation theory. But I think we all agree that if lambda is negative, there must be an imaginary part here, because it must tunnel. Okay? And there's no way you can have an imaginary part if it were convergent, because you would just be summing real terms, and it's convergent, so you just get a real answer. There's no way to get an imaginary part. Moreover, there's no way to get an imaginary exponentially small part from the decay here. And this should be connected to this just by continuation in lambda. So if one of them is divergent, the other one must be divergent. Okay? Yeah, same sort of argument. Very beautiful, very powerful. And the goal that you should keep in mind is, can you do this type of argument in some really non-trivial theory? And this is what we'll talk about in the next couple of lectures, slowly work our way up from these simple examples of differential equations or quantum mechanics. And, okay, yeah. So that's enough for today. Thank you.
Yes, questions? So?
To me, that looks quite similar to Dyson's argument, but why do you say it's a proof and Dyson's one's an argument?
Well, it's not really a proof, right?
So it's the proof of, it's an argument of...
No, okay. So in this case, it's completely clear that on the right-hand side, it's unstable and that there should be imaginary contributions to something you're calculating.
But in QED, but you cannot.
In QED, you can make an argument that if you flip the sign of alpha, it should be unstable. But what did you actually calculate to show that it's unstable? Did you calculate G minus 2 when E squared is negative? What did you calculate?
I'm just asking whether similar kind of calculation can be done in QED.
So both of these arguments I just gave you were explicitly designed to make more concrete Dyson's argument in the QED language. By bringing it to quantum mechanics, you really understand how it works in detail. In QED, we don't really have the same sort of computational capability that we have at this quantum mechanics level. But I mean, at a certain level, yes, it's the same argument.
All right, there is another question.
So the quantum mechanics examples that you showed, does that also belong to these plane leap classes?
Sorry, I can't hear.
So the quantum mechanics example and like deformation of the harmonic potential that you showed, like does that also belong to the plane leap class you said earlier?
What, the plane what?
Plane leap.
Oh,
I
plane
love
leap
it.
equation. Okay.
Plane leap classes.
No.
There is. It told us there is 6 plane leap classes.
No, there's no. I can't write a Painlevé differential equation to describe this problem. But tomorrow you see that I can write a Painlevé equation to describe these matrix model problems. We'll be able to do that in complete detail to see this phase transition, these instabilities, changes of saddles. This is really an infinite dimensional problem here. This is a patentable problem.
Other question?
This is a very stupid question probably, but you mentioned Dyson's argument about QED and said it's very difficult to prove diagrammatically because of signs. Is it proven, or can it be proven for scalar QED?
Yeah,
It's
scalar QD. No,
yeah.
but you get closer.
Okay.
There's still no actual proof.
Okay. But sign problems.
The combinatorics is more complicated because of the gauge structure, the bosons and the charged particles, if you like.
All right. Not anymore?